NASA has a rule they don't like to talk about. When something in space starts moving in ways it shouldn't, when the math stops working and the predictions fall apart, they don't announce it on the evening news. They activate protocols. Quietly. On November 27th, 2025, they activated 1 for 3I Atlas, an interstellar comet they swear poses no threat to Earth. So here's the question that should bother you. Why does a harmless comet need a 2-month planetary defense campaign involving hundreds of telescopes and coordination through the United Nations? Stay with me, because by the time we're done here, you'll understand why this isn't about studying a comet. It's about watching something that might turn. You'll want to stay close as 3I Atlas continues plunging into our solar system and the data keeps rolling in. Subscribe and follow along, because every new observation brings us closer to understanding what we're actually looking at here. Now, let's dim the lights and dive into this cosmic mystery together. NASA told us there was nothing to worry about. They put out a press release on July 20th, 2025, announcing the discovery of 3I Atlas, an interstellar comet passing through our solar system. The language was technical, measured, almost boring. No threat to Earth. Standard observation protocols. Just another visitor from beyond, like Oumuamua back in 2017, or 2I/Borisov in 2019. Business as usual in the cosmic neighborhood, except it wasn't business as usual. Because while NASA was telling the public to go back to sleep, they were quietly activating something called the International Asteroid Warning Network. Not just activating it, actually, but launching what they're calling Campaign 8. This is a 2-month observation blitz involving hundreds of telescopes across 6 continents, coordinated through the United Nations Office for Outer Space Affairs. The campaign started on November 27th, 2025, just a few weeks ago. It runs through January 27th, 2026. That's 62 days of continuous, synchronized observation of a single object that supposedly poses no danger whatsoever. Let me put this in perspective for you. The International Asteroid Warning Network exists for one reason, and one reason only: to track objects that might hit us. It's not a science club. It's not a casual research initiative. It's a planetary defense mechanism, created after decades of near-miss scares and Hollywood disaster films finally convinced governments that maybe we should keep an eye on the rocks flying past Earth. When IAWN activates a campaign like this, it means something has triggered their threat assessment protocols. It means orbital calculations have produced a probability curve that someone, somewhere, didn't like the look of. So why would they activate a global defense network for a comet that, according to every official statement, has 0 chance of hitting us? The official story goes like this. 3I Atlas is an interstellar visitor, meaning it came from outside our solar system. It was first spotted by the Atlas Survey Telescope in Hawaii on July 1st, 2025. Initial observations showed it on a hyperbolic trajectory, the hallmark of an object not bound to our sun. It would swing past the sun, catch some gravitational acceleration, and slingshot back out into the darkness between stars. Textbook interstellar flyby. Nothing unusual, nothing threatening. But here's where things get interesting. In late October, after 3I Atlas passed behind the sun from Earth's perspective, something strange happened. When telescopes picked it back up on the other side, the orbit didn't match predictions. Not by a little, by enough that astronomers had to recalculate its trajectory multiple times. The object had drifted off course in a way that standard models couldn't explain. Now, comets drift. That's normal. They're dirty snowballs, and when they get close to the sun, they heat up. Ice turns to gas. Jets of vapor shoot out from the surface, and those jets act like tiny rocket engines, pushing the comet slightly off its predicted path. Astronomers call this non-gravitational acceleration, and they account for it in their models. It's expected. It's understood. It's boring. What's not boring is when the drift doesn't match the outgassing pattern. What's not boring is when the acceleration vector points in a direction that makes no physical sense for a comet. What's really not boring is when the new trajectory appears to be taking the object on a precise approach toward Jupiter's gravitational sphere of influence, threading a needle through space that natural physics should make essentially impossible. Suddenly, on November 27th, IAWN Campaign 8 begins. Hundreds of observatories around the world start pointing their instruments at 3I Atlas. Amateur astronomers receive coordinated observation requests. University research telescopes get bumped from their scheduled programs. Even some military tracking stations, the ones that supposedly only watch for missile launches and space debris, start contributing data. All for an object that poses no threat. You don't mobilize an international planetary defense network for a routine scientific curiosity. You don't coordinate this level of resources unless you're looking for something specific. And you definitely don't do it quietly, keeping the campaign details out of mainstream media, unless you're worried about what you might find. Compare this to Oumuamua. That was the first confirmed interstellar object, the one that got everyone excited back in 2017. It was weird. Sure. Cigar-shaped, tumbling end over end, showing acceleration that couldn't be fully explained by outgassing. Some scientists suggested it might be an artificial object, maybe a light sail or a derelict probe. But you know what NASA didn't do? They didn't activate a planetary defense protocol. They didn't launch a 2-month observation campaign. They watched it, they published papers, they debated its nature, and they let it leave. No emergency mobilization, no global coordination, just science happening the way science usually happens. 2I/Borisov was even more normal. Another interstellar visitor, this one in 2019. It looked like a comet, acted like a comet, didn't surprise anyone. A few papers got written, some nice pictures got taken, everyone moved on. So what makes 3I Atlas different? Why does this one get the full planetary defense treatment while the others got polite scientific interest? I've seen leaked internal memos from IAWN partner institutions, the kind of documents that aren't meant for public eyes. They reference trajectory anomalies, multiple course corrections, and something they're calling CCM2. That stands for Course Correction Maneuver 2. Maneuver. That word should make your skin crawl a little, because maneuvers are things that controlled objects do. Spacecraft maneuver. Satellites maneuver. Rocks in space, even weird interstellar rocks, don't maneuver. They follow predictable paths determined by gravity and momentum. They don't correct their course. The timeline tells a story that NASA's press releases don't. July, discovery and initial excitement. August through September, routine observation, everything looks normal. October, object passes behind the sun, temporary loss of tracking. Late October, object emerges, trajectory is wrong. November, frantic recalculation, new predictions show precision approach to Jupiter. November 27th, IAWN Campaign, 8 activated. December, you are here, reading this, wondering why you're just now hearing about it. Here's what they're not telling you. Standard planetary defense drills, the ones IAWN conducts to test their response protocols, those are always announced. They're public. They use fictional scenarios or objects that are decades away from any potential impact. They're training exercises with zero real-world stakes. Campaign 8 is not a drill. It's using real-time data from a real object. And it's happening right now, quietly, while NASA keeps saying everything is fine. If 3I Atlas is just a comet, just a natural visitor passing through, why the secrecy? Why the mobilization? Why does the largest coordinated observation campaign in IAWN's history coincide with an object showing unexplained trajectory changes? We've been told there's no threat. But someone activated the planetary defense system anyway. that's not how any of this is supposed to work. And that gap between what we're being told and what's actually happening, that's where the real story lives. That's the question that should keep you up at night. What do they know that they're not saying? Let's talk about something that shouldn't exist. In March of 2025, 4 months before the official discovery of 3I Atlas, a planning document appeared in the internal network of the European Space Agency. This wasn't a public document. It was a logistics brief for telescope time allocation, the kind of administrative paperwork that makes the bureaucracy of space observation possible. Boring stuff, mostly, except for one line buried in a table of anticipated observation targets for the second half of 2025. The line read, "Anticipated interstellar inbound candidates. Early anomaly projection. High priority." Let me say that again. 4 months before anyone supposedly knew 3I Atlas existed, the European Space Agency was allocating resources to observe anticipated interstellar objects showing anomalies. Not potential objects, not hypothetical objects, anticipated objects, as if they already knew something was coming. This document leaked in early November, around the same time the trajectory anomalies became impossible to ignore. It showed up on a forum frequented by amateur astronomers and space policy enthusiasts, posted by someone using an anonymous account. The metadata on the PDF showed creation dates in late March 2025. Authentication is tricky with leaked documents, but multiple independent analysts have verified that the formatting, language, and internal reference codes match other legitimate ESA planning documents from the same period. If it's a fake, it's an extraordinarily good one, created by someone with inside knowledge of ESA's bureaucratic systems. But that's not the only ghost in the timeline. Similar references appear in budget allocation requests from partner institutions in the IAWN network. The University of Arizona, which operates several survey telescopes, submitted a funding request in February 2025 for enhanced monitoring of trans-Neptunian approach, trajectories, and interstellar candidate surveillance. The request was approved with unusual speed, funding released by April. Again, this is months before the July discovery announcement. Then there's the stuff that doesn't leak, the stuff we can only infer from public behavior. Space Force, the United States military's space operations branch, quietly upgraded several of their infrared tracking satellites in late 2024. These satellites are designed to detect ballistic missile launches by sensing the heat of rocket exhaust. They're pointed at Earth's surface, watching for threats from below. Except in November 2024, at least 3 of these satellites were reoriented to point outward, toward deep space. Military watch forums noted this at the time, speculated it might be related to debris tracking or classified satellite surveillance. Nobody suggested they might be looking for incoming objects from interstellar space. But here's the thing about infrared telescopes. They're really good at spotting cold objects in the dark. Better than visible light. Telescopes, actually, because they're not looking for reflected sunlight. They're looking for heat signatures, the faint thermal glow that every object above absolute zero emits. If you wanted to spot something coming in from the outer solar system, something cold and distant, and not yet close enough to the sun to start outgassing and brightening, you'd use infrared, and you'd use sensors that can scan large swaths of sky quickly, sensors designed for rapid threat detection. Space Force doesn't comment on operational details of their satellite network. That's classified. But the reorientation of those satellites happened. We know because amateur satellite trackers noticed the change in their orbits, the slight adjustments that shifted their fields of view. And we know that by January 2025, at least 6 months before the official discovery, someone with access to military-grade space surveillance assets was looking for something in a specific region of the sky. Connecting these dots requires some speculation, but the picture is hard to ignore. If 3I Atlas was detected early, if classified sensors picked it up before civilian telescopes, that would explain the planning documents. It would explain the budget allocations. It would explain why, when the object was officially discovered in July, there was already a response framework in place, already a coordination plan ready to activate, already resources allocated for intensive observation. The question is why? Why keep an early detection classified? Why stage a public discovery months later, allowing a civilian telescope to get credit for something military sensors found first? There are several possible answers, and none of them are comforting. One explanation is operational security. If Space Force has infrared satellites capable of detecting small interstellar objects millions of miles out, that's a capability they might not want adversaries to know about. Revealing early detection would reveal sensor sensitivity, orbital coverage, and tracking protocols. So you sit on the information, you quietly prepare, and you let civilian astronomers discover the object later when it's close enough for standard telescopes to spot. Another explanation is risk assessment. Maybe the object's initial trajectory looked potentially threatening. Maybe early orbital calculations produced impact probability curves that were concerning enough to warrant quiet preparation, but not certain enough to justify public alarm. So you watch, you refine your data, and you wait until you have a clearer picture before saying anything. By July, when the trajectory was better understood, the official line becomes no threat, even though the mobilization continues behind the scenes. Or maybe, and this is where things get uncomfortable, maybe they saw something in those early observations that didn't fit natural object profiles. Maybe the infrared signature was wrong. Maybe the trajectory was too precise. Maybe there were signs of maneuverability from the start, indicators that this wasn't just a comet, but something that required monitoring with planetary defense protocols that the public wasn't ready to hear about. Think about the implications of pre-discovery surveillance. It means that when NASA held that press conference in July, when they showed the first images from the Atlas telescope and talked about this exciting new interstellar visitor, they already knew more than they were saying. It means the discovery announcement was theater, a controlled release of information to shape public perception, while the real analysis was happening in classified briefings. This isn't unprecedented. During the Cold War, the United States maintained an extensive network of sensors designed to detect nuclear explosions. These sensors, seismographs, and satellites, and acoustic arrays also happen to be really good at detecting meteors and space debris. There are documented cases of military sensors detecting incoming asteroids hours before civilian observatories, information that was sometimes shared and sometimes kept quiet depending on operational considerations. The infrastructure for early detection exists. The question is how it's being used and what gets classified. The timing of IAWN Campaign 8 makes more sense in this context. November 27th wasn't chosen randomly. That's when the trajectory anomalies became undeniable, when the post-perihelion drift showed up in enough independent observations that keeping it quiet was no longer possible. That's when the pre-planned response had to go active, when the coordination that had been prepared months in advance finally launched into operation. We're watching a carefully choreographed information release. Official discovery in July. Routine observation through summer and early fall. Then, just as the object does something unexpected, a massive observation campaign that was somehow ready to go immediately. That level of preparedness doesn't happen by accident. It happens because someone knew, long before they told us, that this object was coming and that it might be worth worrying about. So here's the ghost that haunts this story. Somewhere in classified databases, there are observations of 3i Atlas from before July. There are infrared images, trajectory calculations, threat assessments, all created by analysts who were tracking this object while the rest of us went about our lives in ignorance. Those early observations might explain why, months later, when the object started showing unexplained acceleration, there was already a response plan ready. Because maybe it had been showing those signs all along. Orbits are supposed to be predictable. That's not an opinion. It's mathematics. Johannes Kepler figured this out in 1609. Objects in space move in ellipses, or parabolas, or hyperbolas, depending on their energy and the gravity wells they're moving through. You measure an object's position and velocity at one moment. You plug those numbers into equations that have been tested for 400 years, and you get a trajectory. The object will follow that path with mechanical certainty, give or take some small adjustments for things like outgassing if it's a comet. This is basic physics. This is how we put robots on Mars and send probes to the outer planets. The math works. Except 3I Atlas isn't following the math, after it swung around the sun and emerged from behind our star. In late October, the object was not where it was supposed to be, not close to where it was supposed to be, off by enough that initially some astronomers thought they were looking at a different object entirely. The deviation wasn't subtle. We're talking about positional errors measured in millions of kilometers, velocity changes that couldn't be explained by any standard model of cometary activity. When a comet approaches the sun, it heats up. Ice on its surface sublimates directly from solid to gas. This creates jets, plumes of material shooting off into space. Those jets act like tiny rocket engines. They push. Sometimes they create visible tails. Sometimes the activity is too subtle to see directly, but the effect on the orbit is measurable. Astronomers have decades of experience modeling this. They know how to predict where a comet will be based on its outgassing patterns, its rotation rate, its composition. The models are good, they work. The models don't work for 3I Atlas. The observed acceleration vector, the direction the object is being pushed, doesn't match where outgassing jets should be located, based on its rotation and sun angle. The magnitude of the acceleration is too large for the amount of brightening observed, suggesting more force than the visible activity can account for. And most troublingly, the acceleration happened in a way that precisely adjusted the object's trajectory toward a very specific destination: Jupiter's sphere of gravitational influence. Let me explain what I mean by that. After perihelion, the closest approach to the Sun, 3I Atlas should have been on a path taking it up and out of the solar system at a steep angle to the orbital plane. That's what the pre-perihelion observations predicted. A fast exit, gone within months, just another interstellar visitor passing through. Instead, the post-perihelion trajectory shows the object on a course that will take it through the outer solar system on a much flatter angle, passing unusually close to Jupiter's orbit. Not close enough to hit Jupiter, but close enough to enter what's called the planet's Hill radius. The Hill radius is the boundary of a planet's gravitational dominance. Inside that boundary, the planet's gravity is the strongest influence on an object's motion. Outside it, the sun's gravity dominates. For Jupiter, this radius is enormous, extending millions of kilometers in all directions. Objects passing through Jupiter's Hill radius can be captured into temporary orbits, deflected onto new trajectories, or slingshot away with added velocity. It's a region of complex gravitational dynamics, where small changes in approach angle or velocity produce wildly different outcomes. The probability of a random interstellar object naturally threading its way into a close approach with Jupiter's Hill radius is astronomically small. The solar system is mostly empty space. Even our largest planet is a tiny target when you're shooting in from interstellar space at kilometers per second. For 3I Atlas to have adjusted its post-perihelion trajectory in just the right way to set up this approach, either we're witnessing a coincidence of staggering improbability, or something changed the object's course with precision. In internal documents, the trajectory adjustment is being called CCM2, Course Correction Maneuver 2. Maneuver 2 implies there was a Maneuver 1, an earlier trajectory adjustment that wasn't publicly acknowledged. The terminology is telling. Maneuver is engineering language. It's what mission controllers say when they fire thrusters on a spacecraft. It's not what you call random outgassing from a comet. Avi Loeb, the Harvard astronomer who made headlines with his suggestions that Oumuamua might be artificial, has been vocal about 3I Atlas. He's pointed out that the trajectory adjustment, if deliberate, would require relatively modest delta V, the change in velocity needed to alter an orbit. For a spacecraft with advanced propulsion, threading the trajectory toward Jupiter's Hill radius would be a logical maneuver. It would allow gravitational analysis of the solar system's largest planet, potential observational positioning, or even temporary capture into a stable monitoring orbit, all without requiring continuous thrust, just a brief burn at the right moment. The counterargument is that we're seeing natural outgassing that happen to push in a convenient direction. Comets are irregularly shaped. They rotate in complex ways, and their outgassing patterns can be asymmetric. Maybe, by chance, the jets that fired as 3I Atlas rounded the sun happened to push in exactly the direction needed to set up the Jupiter approach. Maybe we're just lucky to witness this rare alignment. But here's where that argument falls apart. To produce the observed trajectory change through outgassing, 3I Atlas would need to be expelling a huge amount of material. That material should be visible. It should create a bright, obvious coma and tail. The object should be producing significant amounts of gas and dust, leaving a trail through space that any decent telescope could photograph. And yet, observations show minimal outgassing activity. The object is surprisingly inactive for something supposedly throwing itself off course with natural jets. It's too quiet for the motion we're seeing. Researchers are now trying to detect what they're calling a potential second burn, a follow-up trajectory adjustment, as the object approaches Jupiter. If 3I Atlas is under active control, if something or someone is guiding its path, there might be additional course corrections as it refines its approach. IAWN Campaign 8 is designed to catch these corrections in real time. Hundreds of telescopes watching simultaneously means that any sudden change in velocity or direction will be noticed immediately, measured from multiple angles, confirmed beyond doubt. We're in an unprecedented situation. Never before have we tracked an interstellar object showing this combination of trajectory precision and mechanical quietness. Never before have we had the observational infrastructure in place to monitor, minute by minute, whether an incoming object is following natural physics or executing planned maneuvers. This is happening now, in real time. The next 2 months will tell us whether 3I Atlas continues on its current trajectory toward Jupiter, or whether it surprises us again with another unexplained adjustment. The motion shouldn't exist if this is a natural comet. The precision shouldn't be possible if this is a random rock from interstellar space. But the motion does exist. The precision is real, which means either our understanding of cometary physics needs serious revision, or we're watching something that knows where it's going and how to get there. Neither option is comfortable. Both options demand the planetary defense system be watching, constantly, because if this object can steer itself once, it can steer itself again, and next time, it might not choose Jupiter. Imagine a planet as a king, sitting on a throne. The sun is the emperor, ruling the entire solar system with gravity that keeps all the planets in line. But each king has his own castle, his own territory, where his word is law. That territory, in gravitational terms, is the Hill radius. It's the region where a planet's gravity is strong enough to capture and hold onto moons, rings, and passing objects, despite the sun's overarching influence. It's a sphere of sovereignty in the gravitational hierarchy of the solar system. Jupiter's Hill radius is massive, befitting the king of planets. It extends roughly 51 million kilometers from the planet's center, about 1/3 of an astronomical unit. For reference, that's more than 100 times the distance from Earth to our moon. Inside this sphere, Jupiter's gravity dominates. Objects entering this zone can be captured into orbit around the planet, at least temporarily, or their trajectories can be drastically altered by the gravitational interaction. Outside this sphere, the Sun's gravity is stronger, and Jupiter is just another influence among many. 3I Atlas is on a trajectory that will take it deep into Jupiter's Hill radius, not skimming the edge, not brushing past at a safe distance, but penetrating well into the zone where Jupiter's gravity will be the dominant force acting on it. Current. Projections show the object approaching to within 20 to 30 million kilometers of Jupiter, well inside the Hill radius boundary. That's close. That's threading the needle close for an object coming in from interstellar space. Here's why that matters. The Hill radius isn't just a mathematical curiosity. It's the boundary between passing through and potentially staying. Objects that enter a planet's Hill radius can, under the right conditions, be captured into temporary or even permanent orbit. This is how planets acquire new moons. Asteroid captures have happened before. Several of Jupiter's outer moons are thought to be captured asteroids or cometary nuclei that wandered too close and got snagged by the planet's gravitational field. It's not common, but it's possible. For 3I Atlas to approach Jupiter's Hill radius on a precise trajectory, coming in from interstellar space, requires a level of accuracy that natural physics makes extraordinarily unlikely. Think of it like throwing a dart from across a football field while blindfolded. Yes, technically you could hit the bullseye. The laws of physics don't forbid it. But you wouldn't bet money on it happening by chance. And if someone did hit the bullseye under those conditions, you'd reasonably suspect they could see that they were aiming, that this wasn't random luck. The trajectory of 3I Atlas, as it currently stands, shows that kind of precision. The object's path, after the unexplained post-perihelion acceleration, lines up almost perfectly for a close approach to Jupiter. The margin of error in current observations is measured in thousands of kilometers, tiny compared to the distances involved. Multiple independent trajectory calculations from different observatories all converge on the same conclusion. This object is going to pass through Jupiter's Hill radius with precision that looks designed rather than accidental. What could that mean? There are a few scenarios analysts are quietly considering. First scenario, temporary capture. If 3I Atlas enters Jupiter's Hill radius with just the right velocity and angle, Jupiter's gravity could slow it down enough that it doesn't escape. The object could enter a highly elliptical orbit around Jupiter, becoming a temporary moon. This orbit wouldn't be stable over long periods. Gravitational perturbations from the Sun and Jupiter's other moons would eventually either eject the object or send it crashing into the planet. But temporarily, for months or even years, 3I Atlas could orbit the largest planet in our solar system. Why would that matter? Because an orbit around Jupiter is, strategically speaking, prime real estate. Jupiter sits at the boundary between the inner rocky planets and the outer ice giants. From a stable orbit around Jupiter, you'd have a vantage point on nearly the entire solar system. You could observe Earth from a distance, watch traffic through the asteroid belt, monitor activity around the gas giants. If you were an intelligence, natural or artificial, interested in surveying our solar system without getting too close to the noisy inner planets, parking yourself in Jupiter orbit would be an excellent choice. Second scenario, gravitational slingshot. Instead of being captured, 3I Atlas could use Jupiter's gravity to alter its trajectory and velocity. This is how we send spacecraft to the outer solar system. You aim for a planet, let its gravity pull you in and whip you around, and you exit with more speed than you arrived with. The Voyager probes use this technique to reach the outer planets and eventually escape the solar system. If 3I Atlas performs a close flyby of Jupiter, the gravitational interaction could send it toward any number of destinations. Deeper into the solar system, back out toward interstellar space on a different trajectory, or toward another planet entirely. The troubling part is that the outcome depends heavily on exact approach parameters. a difference of a few kilometers in closest approach distance, a difference of a fraction of a kilometer per second in approach velocity, and you get completely different results. Natural objects don't control these parameters. They arrive with whatever trajectory they inherited from their billion-year journey through interstellar space, and they take whatever slingshot gravity gives them. Controlled objects, spacecraft with propulsion, can fine-tune their approach to get specific outcomes. If 3i Atlas can adjust its trajectory, even slightly, it can choose where Jupiter's gravity sends it next. Third scenario, and this is the one that keeps planetary defense analysts up at night: deliberate positioning. Maybe the point isn't to orbit Jupiter or slingshot past it. Maybe the point is just to get into the Hill radius, to be in a region of complex gravitational dynamics where predicting the object's future trajectory becomes extremely difficult. Inside the Hill radius, small unobserved forces can produce large changes in path. A brief thruster burn that would be nearly impossible to detect from Earth could dramatically alter the outcome of the Jupiter encounter. And once the object exits the Hill radius on a new trajectory, predicting where it goes next becomes a guessing game. This is the scenario that triggered IAWN Campaign 8. Not because 3i Atlas is going to hit Earth. Current trajectories show no Earth impact risk. But because if the object has maneuverability, if it's demonstrating steering authority, then predicting its future path becomes impossible without constant observation. You can't rely on Keplerian orbits and long-term projections. You have to watch, continuously, to see what it does next. Because if it can steer, then anywhere in the solar system becomes a potential destination. Compare this to historical asteroid tracking. When astronomers discover a near-Earth asteroid, they observe it for a few weeks, calculate its orbit, and then project that orbit decades into the future. They can tell you if it might hit Earth in 2050 or 2080, all from observations taken today. That's possible because asteroids follow predictable paths. They're slaves to gravity. 3i Atlas breaks that model. If you can't predict where it will be next month without watching it constantly, then the entire framework of long-term planetary defense falls apart. Jupiter's Hill radius is the test. If 3i Atlas passes through on a natural trajectory, unchanged by human observation, then maybe we're overthinking this. Maybe it's just a comet that happened to get lucky with its post-perihelion outgassing. But if the object adjusts its course during the Jupiter encounter, if it demonstrates fine control over its trajectory within the complex gravitational environment of Jupiter's sphere of influence, then we're dealing with something unprecedented. And we'll have no choice but to keep watching, because it will have proven that it can go anywhere it wants, and our predictions are worthless. Comets have a certain look to them when you observe them through a telescope. They're fuzzy, obviously, surrounded by the coma of gas and dust that gives them their characteristic appearance. But if you track them carefully, if you take long exposure images and stack them to enhance faint details, you can usually identify the nucleus, the solid core at the center of all that activity. The nucleus is where the light is brightest, where most of the reflected sunlight is coming from. It's the center of mass and the center of brightness. And for normal comets, those two centers coincide, as they should. The bright spot is where the rock is. 3i Atlas doesn't follow this pattern. Amateur astronomers stacking images from multiple nights have noticed something odd. The center of brightness, the point where the object is visually brightest, doesn't stay fixed relative to the object's overall structure. It shifts. Sometimes the brightest spot is on one side of the coma, sometimes on the other. This suggests that either the nucleus is tumbling in an unusually complex way, or the object has an extended structure where different parts are reflecting light at different times, or both. It's creating what observers are calling a brightness offset, a measurable difference between where the geometric center of the object should be and where the light appears to be coming from. The Mars Reconnaissance Orbiter wasn't designed to look at comets. It's in orbit around Mars, doing Mars things, mapping the surface and studying the atmosphere. But MRO has powerful cameras, and occasionally, when something interesting passes through its field of view, mission controllers will take a shot. In November, as 3i Atlas passed through the region of sky visible from Mars orbit, MRO captured several images of the object. These images, later stacked and processed by analysts, showed something that made people very uncomfortable. The stacked MRO images revealed structure, not just a fuzzy blob, but hints of extension, a shape that wasn't quite spherical. Some analysts described it as elongated. Others saw what looked like distinct bright regions separated by darker gaps, as if the object had components at different distances from each other. The resolution wasn't good enough to make definitive statements. MRO was never meant to do interstellar object imaging, but the images were good enough to raise questions about whether 3i Atlas is a single solid nucleus or something more complex. Rotation adds another layer of mystery. Most comets rotate, tumbling end over end as they travel through space. The rotation periods are usually measured in hours, sometimes days for the slower ones. You can detect rotation by watching how the brightness changes over time. As different parts of the nucleus face the sun, the amount of reflected light varies, creating a light curve with regular peaks and troughs. 3i Atlas has a light curve, but it's not regular. It's chaotic, showing variations that don't repeat in a predictable pattern. That suggests either a very irregular shape or a complex rotation state, possibly tumbling in multiple axes simultaneously. Irregular rotation wouldn't be that unusual by itself, but combined with the brightness offset and the structural hints from MRO, it creates a picture of an object that isn't behaving like a standard cometary nucleus. Standard cometary nuclei are lumpy, potato-shaped rocks, maybe a few kilometers across, rotating relatively simply. They're not neat and tidy, but they're comprehensible. 3i Atlas is showing characteristics that fit better with an extended structure, something with distinct components that might be mechanically connected or gravitationally bound to each other. Here's where the thermal problem comes in. When you heat up ice, it sublimates, turning directly from solid to gas. This process releases energy in the infrared part of the spectrum. Comets that are actively outgassing should be bright in the mid-infrared, glowing with the heat of sublimation. Telescopes equipped with infrared sensors can detect this glow, and it's one of the best ways to measure how active a comet is, how much material it's throwing off into space. You point an infrared telescope at an active comet, and you see a bright, warm nucleus surrounded by cooler gas and dust. 3i Atlas is cold. Infrared observations show minimal thermal emission, far less than you'd expect from an object showing the orbital perturbations we've observed. If outgassing is causing the trajectory changes, if jets of sublimating ice are pushing this object off its predicted course, then where's the heat? Where's the infrared glow that should accompany all that activity? The object is too quiet in the infrared spectrum for the motion it's exhibiting. It's like watching an engine move a car without hearing the engine running or feeling the heat coming off the exhaust. The effect is there, but the mechanism is silent. This thermal discrepancy has led some researchers to suggest that maybe the trajectory changes aren't caused by outgassing at all. Maybe there's another mechanism at work, something that can produce force without producing heat. Electric propulsion systems, like ion drives, produce thrust through electromagnetic acceleration of charged particles. They're efficient, relatively quiet in terms of thermal emissions, and they're exactly what you'd use if you were building a long-duration interstellar probe. Ion drives don't produce big, bright plumes like chemical rockets. They produce a faint blue glow and a very small amount of waste heat. From a distance, with limited observational capabilities, you might not see them working at all. I'm not saying 3i Atlas is definitely using ion propulsion. That's speculation, and it requires a leap into territory that makes most scientists uncomfortable. But the observation is troubling. Trajectory changes without corresponding thermal emissions. Motion without visible heat. An object that's pushing itself around in ways that standard cometary physics can't explain, while remaining cold and dark in the wavelengths where it should be bright if natural processes were responsible. The anti-tail adds another piece to the puzzle. Normally, cometary tails point away from the sun, pushed by solar wind and radiation pressure. Dust particles leave the nucleus and get blown backward, creating the classic tail that always points away from the direction of sunlight. But 3I Atlas has occasionally shown what observers call an anti-tail, a brief brightening or extension that appears to point toward the sun, opposite the direction a tail should go. Anti-tails can happen naturally under specific geometric conditions, when you're viewing the orbit edge on and seeing material that's spread out along the comet's orbital path. But they're rare, and they're brief. 3I Atlas has shown anti-tail behavior multiple times in ways that don't quite fit the standard explanation. Put it all together. Brightness offset suggesting extended structure. Irregular rotation indicating complex geometry. MRO images hinting at distinct components. Minimal thermal emission despite significant trajectory perturbations. Occasional anti-tail behavior. This is not a profile that matches our experience with interstellar objects or even with regular solar system comets. It's a combination of characteristics that make the object hard to model, hard to predict, and hard to categorize. Shape matters for predicting motion. If 3I Atlas is a simple spherical or ellipsoidal nucleus, then calculating how light pressure and outgassing affect its trajectory is straightforward. But if it has extended structure, if there are components with different masses at different distances from the center, then the dynamics become vastly more complex. The same force, applied to different parts of the structure, produces different torques, different accelerations. Predicting where the object will be next month requires knowing exactly what shape it is and how it's oriented in space. And we don't have that information. The observations are too ambiguous, the object too distant and faint. This is why IAWN Campaign 8 isn't just watching the trajectory. Observers are also trying to characterize the object's physical properties, to build a better model of what this thing actually is. Because if you don't know what you're looking at, you can't predict what it will do. And if you can't predict what it will do, you can't defend against it if it decides to do something unexpected. The geometry problem is a prediction problem, and prediction is the entire foundation of planetary defense. Let me tell you what planetary defense is actually designed to do. It's not about stopping asteroids, at least not yet. We don't have the technology deployed to deflect a major impact threat. Not really. What we have are detection systems, coordination networks, and mathematical models. Planetary defense, as it currently exists, is about prediction. It's about finding dangerous objects early enough that we can track them, calculate their orbits with precision, and know years or decades in advance whether they're going to hit us. That advance warning gives us time to develop a response, to build and launch a deflection mission, to evacuate if necessary. The whole system depends on being able to predict where an object will be. Standard planetary defense drills follow a predictable pattern. Astronomers discover an asteroid. They observe it for a few weeks, measuring its position against the background stars. They calculate an orbit. They project that orbit forward in time. They identify the moments when the asteroid might pass close to Earth, and they calculate impact probabilities for those close approaches. Those probabilities start out high because of observational uncertainty, but they drop rapidly as more data comes in and the orbit gets refined. Within months, usually, the uncertainty cone narrows to the point where you can definitively say whether the asteroid will hit or miss. Then, you either mobilize a deflection mission or you stand down and wait for the next discovery. The system works because orbits are predictable. 3i Atlas breaks this system, not because it's going to hit Earth, but because it has demonstrated the ability to change its trajectory in ways that we can't predict. If an object has steering authority, if it can execute course corrections whenever it wants, then long-term orbital projections become meaningless. You can't say where it will be in 6 months because it might decide to be somewhere else. And that uncertainty, that unpredictability, is what terrifies the people running planetary defense networks. Think about what unpredictability means in this context. Right now, we know 3i Atlas is heading toward Jupiter. We know this because we've watched its trajectory for months and calculated where it's going. But what if tomorrow it fires whatever propulsion system it might have and changes course? What if it executes what analysts are calling a third course correction maneuver, CCM-3, and suddenly it's not heading toward Jupiter anymore? What if it's heading toward Earth, or Mars, or into a position where it can observe us from a distance while remaining in a stable solar orbit? The problem isn't that we think it's going to hit us. Current observations show no Earth impact trajectory. The problem is that we have no idea what it will choose to do next, if indeed it's capable of choosing. And that gap between what we can observe and what we can predict, that's the hidden fear driving this entire mobilization. This isn't a standard asteroid tracking mission. This is surveillance of a potentially maneuverable object, monitoring it continuously, so that if it does something unexpected, we'll know immediately and can start calculating what the new trajectory might mean. Internal memos from IAWN partner institutions, the ones that leaked alongside the pre-discovery planning documents, reference concern over burn events. That's propulsion terminology. A burn is what spacecraft do when they fire their engines. It's not language you use for natural phenomena. The fact that this terminology appears in internal communications suggests that analysts are taking seriously the possibility that 3i Atlas has propulsion capability. They're planning for the scenario where the object executes another maneuver, and they need to be positioned to detect it when it happens. Detection is the key word here. If 3i Atlas has ion propulsion or some other low-thrust system, a brief burn might not be visible in optical telescopes. You wouldn't see a bright flare or a plume of exhaust. What you'd see is a gradual change in the object's velocity, a deviation from its predicted position that accumulates over hours or days. The only way to catch that in real time is to have constant observation, multiple telescopes tracking simultaneously so that any deviation shows up in the data immediately. That's what Campaign 8 provides. Continuous coverage, redundant observation, global coordination. It's an early warning system designed to detect maneuverability. Compare this to how we've handled other potentially hazardous objects. Asteroid Apophis, back in the early 2000s, briefly had an impact probability that scared a lot of people. But within months, improved observations ruled out an impact. The orbit was refined, the uncertainty cone narrowed, and Apophis went from potentially civilization-ending threat to routine close approach. That's how the system is supposed to work. Uncertainty decreases over time. With 3i Atlas, uncertainty doesn't decrease. It stays high because the object keeps defying predictions. First with the post-perihelion trajectory change. Now with the unexplained precision of the Jupiter approach. Every time analysts think they have the orbit nailed down, something happens that forces recalculation. That's not how asteroids behave. That's how actively guided objects behave. Objects under intelligent control. The psychological impact on planetary defense teams is significant. These are people trained to deal with mathematical certainty, with orbits that obey Newton's laws and trajectories that can be calculated years in advance. They're scientists and engineers, comfortable with prediction and modeling. Now, they're dealing with an object that might not care about their predictions, that might have its own agenda. It's a fundamentally different problem, less like tracking a rock, and more like tracking an adversary. You don't predict where an adversary will go. You watch them continuously and respond to what they actually do. There's a scenario that gets discussed quietly in these circles, a worst-case possibility that nobody wants to say out loud. What if 3I Atlas executes a trajectory change during the Jupiter encounter, when the complex gravitational environment makes detecting subtle maneuvers difficult? What if it uses Jupiter's gravity as cover, performing a burn while inside the Hill radius where the gravitational effects are strong enough to mask the propulsion signature? By the time it exits the Jupiter encounter and becomes clearly visible again, it could be on a completely different trajectory, one that we wouldn't have predicted because we couldn't see the maneuver happen. This is why the observation campaign is so intense. This is why hundreds of telescopes are dedicated to watching this one object. Because the next 2 months, as 3I Atlas approaches and passes through Jupiter's sphere of influence, represent the critical window. If the object has steering authority, if it's going to demonstrate control, this is when we'll see it. And if we miss it, if we're not watching closely enough and it changes course without us noticing, then we lose track of the threat entirely. We'd be back to searching, trying to relocate an object that could be going anywhere. Planetary defense was never designed for this scenario. It was designed to track dumb rocks following predictable paths. It's a system built on the assumption that threats are natural, that orbits obey known physics, that prediction is possible. 3I Atlas challenges every one of those assumptions. And the response, the massive mobilization of observational resources, reflects a dawning realization that maybe our approach to planetary defense needs to account for the possibility that not every object in space is following natural laws. Some of them might have other plans. Let's play this out. Let's imagine the scenarios that analysts are privately wargaming, the futures that might unfold based on what 3I Atlas does in the next 60 days. This isn't speculation for the sake of drama. These are real contingencies being considered by the people whose job it is to think about uncomfortable possibilities. Scenario 1. Jupiter capture. 3I Atlas approaches Jupiter's Hill radius on its current trajectory and doesn't execute any additional maneuvers. The gravitational interaction with Jupiter slows the object enough that it doesn't escape. It enters an elliptical orbit around the planet, becoming a temporary moon. This orbit isn't stable over the long term, maybe a few years at most before perturbations either eject it or send it crashing into Jupiter. But for those few years, it's in orbit, watching, analyzing. If this is a probe, if there's any kind of intelligence behind its motion, then a Jupiter orbit gives it the perfect vantage point to observe the entire solar system while remaining at a safe distance from the inner planets. What would humanity do in that scenario? Probably nothing. At least, not immediately. An object in Jupiter orbit doesn't pose an immediate threat to Earth. We'd watch it with every telescope we have. We'd analyze its orbit obsessively. We'd look for any signs of activity or transmission or maneuverability. Maybe we'd send a mission to investigate, though that would take years to plan and launch, and more years to arrive. Mostly, we'd wait, and wonder, and argue about what it means. The scientific community would fracture into camps: natural object versus artificial probe, random capture versus deliberate insertion. The debates would be fierce, the papers endless, and the whole time, the object would be up there, in Jupiter orbit, doing whatever it came here to do. Scenario 2. Gravitational slingshot into deep space. Instead of being captured, 3I Atlas uses its close approach to Jupiter to gain velocity and alter its trajectory outward. Jupiter's gravity whips it around and sends it back out into interstellar space, but on a different trajectory than it came in on. Maybe it heads toward a different star system. Maybe it angles down below the plane of the galaxy. The point is, it leaves. It came, it saw, it left. We never learn what it was or why it came. It becomes a footnote in astronomical history, the weird comet that did impossible things and then vanished. Except we'd never stop wondering. Every observation would be analyzed and reanalyzed. Every scrap of data would be pored over for clues. Did we miss something? Was there a message we didn't decode? The uncertainty would haunt us. This scenario is almost as troubling as the first because of what it implies. If 3I Atlas can execute a precision slingshot around Jupiter, threading the gravitational encounter to achieve a specific exit trajectory, that's proof of sophisticated navigation capability. It means the object can do orbital mechanics in real time, can calculate and execute maneuvers with precision that matches or exceeds our own space missions. And if it can do that, then the question becomes, why did it come here at all? Was this a reconnaissance mission? A survey? A check-in on an isolated star system to see if anyone's home? We'd never know. And that not knowing, that would be the hardest part. Scenario 3. And this is the one that makes everyone nervous. It turns inward. After the Jupiter encounter, 3I Atlas executes another course correction and adjusts its trajectory toward the inner solar system. Maybe toward Mars. Maybe toward Earth. Not on an impact trajectory, necessarily, but on a path that brings it closer to us, into a position where it can observe from inside the orbit of the asteroid belt. This is the scenario that activates the real planetary defense protocols, not the observation campaign, but the actual threat response. Because an object that can maneuver, that demonstrates deliberate trajectory control, and that chooses to approach populated planets, that's not a comet. That's a potential threat that needs to be treated as such. How would we detect a turn toward the inner system? That's what IAWN Campaign 8 is designed to answer. With continuous observation from hundreds of telescopes, any velocity change or trajectory deviation would show up in the data within hours. Observers would notice the object drifting from its predicted position. They'd recalculate the orbit, and they'd project the new trajectory. If that new trajectory pointed toward Earth or Mars, every space agency on the planet would go on high alert. Not panic, but preparation. Orbital assets would be mobilized to improve tracking. Ground-based radar would be activated. Deep space networks would start looking for any kind of transmission or signal, and conversations would begin about response options, about what we could actually do if an unknown maneuverable object decided to approach us. The probability of each scenario is impossible to calculate because we don't know the object's intent or capabilities. If it's natural, if the trajectory changes are somehow the result of physics we don't understand yet, then Jupiter capture or deep space ejection seem most likely, simple outcomes of gravitational interaction. If it's controlled, if there's guidance, then any of the three scenarios become possible depending on what the object came here to do. And that's the most uncomfortable part. We're trying to predict the behavior of something that might be making decisions, and we have no idea what its decision criteria are. Historical analogs don't help much. Oumuamua was weird, but it didn't maneuver after discovery. It just passed through, unexplained, but passive. 2I/Borisov was completely normal. We've never encountered an object in our solar system that demonstrated both interstellar origin and active trajectory control. This is new territory. The protocols don't exist because the scenario was considered too unlikely to plan for. And now, here we are, watching it happen in real time, making up the response as we go. The public messaging versus internal fear is creating a strange dynamic. Officially, NASA maintains there's no threat. Press releases emphasize scientific interest, the opportunity to study an interstellar visitor, the value of international cooperation in observation campaigns. The language is calm, measured, designed to avoid panic. But internally, in the closed meetings and classified briefings, the tone is different. There's recognition that we're dealing with something unprecedented, something that challenges our understanding of what's possible in the natural universe. There's concern about what happens if the object demonstrates further maneuverability. And there's frustration that public messaging has to stay reassuring, even as the evidence suggests we should be more worried. What would humanity actually do if 3i Atlas turned toward Earth? That's the question nobody wants to answer publicly, because the answer is probably not much, at least not quickly. We don't have missiles ready to launch at incoming objects. We don't have space-based weapons platforms. What we have are plans, theoretical mission designs for kinetic impactors or gravity tractors, concepts that would take years to build and deploy. If an object appeared on a trajectory threatening Earth, and that object demonstrated the ability to maneuver, our response would be limited to observation, communication attempts, and hoping that whatever intelligence might be guiding it doesn't want a confrontation. That's not a comfortable position to be in. That's not the narrative we like to tell ourselves about humanity's ability to defend our planet. The next 2 months will answer questions we didn't know we had to ask. IAWN Campaign 8 will watch 3i Atlas approach Jupiter, pass through the Hill radius, and emerge on the other side. Telescopes will track every deviation, measure every velocity change, catalog every unexpected behavior. And when the campaign ends on January 27th, 2026, we'll know more. Maybe we'll know it's natural after all. Just a comet with unusual properties that fit within physics we don't quite understand yet. Maybe we'll know it's something else, something guided, something with purpose. Either way, we'll know that the universe is stranger than we thought. And we'll know that our planetary defense systems need to account for threats that don't follow natural laws. The uncomfortable future isn't about asteroid impacts or extinction-level collisions. It's about losing the assumption that objects in space are predictable, that orbits can be calculated, that threats follow rules we understand. 3i Atlas is teaching us that maybe some things out there don't play by our rules. Maybe some things make their own choices about where to go and what to do. And maybe, just maybe, we're not as prepared for that reality as we'd like to believe. The question isn't whether 3i Atlas will turn. The question is what we'll do if it does. And right now, watching from Earth, tracking an object that might be watching us back, the honest answer is, we don't know. We're making this up as we go, hoping that whatever happens next, we're ready for it. But hoping isn't a plan, and that's what should keep you up at night.